All right, well, thank you for the introduction. I'm going to jump into my slides here by telling you something about transport layer security, TLS, and then I'll get to what PQConnect does. So TLS is a general purpose mechanism of adding security. At least the idea is it's supposed to add security to all sorts of different protocols, all sorts of different applications. For example, there's lots of software on the internet which is sending and receiving email with SMTP, the Simple Mail Transfer Protocol. And that standard for SMTP does not include security, but there's another standard saying how you can integrate TLS, transport layer security, into SMTP for sending mail encrypted. And then another example, HTTP, the Hypertext Transfer Protocol, does not, in the basic standard, include any security. But TLS has a way to integrate into that, which is, well, HTTPS. And that's something which lots of web browsers and other web clients and web servers support. Sounds good. But if you look at the reality of TLS, then you start seeing some problems. I'm going to start with some slides on examples, and there's lots of these examples. I've just selected some examples of software vulnerability announcements involving TLS. So the first one here is for some robot vacuum cleaners from a company called Dream. And these, at least my first reaction to this is, wait, security for a vacuum cleaner? But well, these are connected vacuum cleaners. And I mean, you're supposed to control the vacuum cleaner with your phone. And if you think about it for a moment, imagine an attacker who's doing industrial espionage. They're going to maybe try to start by breaking into your router in the room, but the router does not have a lot of different ways to sense its environment except for the network. But maybe they can turn that control over the router into control over some devices which have, for example, some audio or video or radar input, as vacuums these days tend to do. And a vacuum is something you expect to be hanging around in your room, so it's great industrial espionage device. Anyway, so these robot vacuums got security certification, but despite that, had this vulnerability announcement saying, sorry, because of mismanagement of TLS certificates, it's possible for attackers who are in the middle, for instance, your network router, in between the vacuum, the communication between your vacuum cleaner and your phone, attackers can steal your secrets and then presumably take over the vacuum cleaner. They didn't go through a lot of details of what the attacker could do starting from this. They just said vulnerability announcement and you really have to upgrade. Another example, these certificate problems show up in lots and lots of TLS vulnerability announcements. For example, Vault and Vault Enterprise, these are some sort of security tools aimed at corporations. And well, their TLS certificate authentication did something wrong. And the result was that an attacker, they say, may be able to craft a malicious certificate that could be used to impersonate another user. These things are always downplayed. The reality is, yeah, an attacker who knows what he's doing can, of course, do this and take over your Vault enterprise for your corporation. Another example, Checkmate is this general purpose monitoring tool for all your different applications in whatever organization. And vSAN, well, I haven't experienced that myself, but I assume it's some way that you can within VMware do your storage area network for storing all your data. And then, well, there's apparently a plugin for Checkmate, which is monitoring your storage area networks with this vSAN software. And well, attackers can intercept traffic because of, again, another certificate issue. And it keeps going like this, not always with certificates. For example, or at least not just failing to check certificates. Embed TLS is a TLS library which had a buffer overflow, so conventional kind of software security problem in parsing. Well, PEM originally, the name stands for Privacy Enhanced Mail. This is originally a way to send around mail with encryption. It's not very popular for that these days, but it has a lot more uses in just generally how you're handling security, along with lots of other standards. And it's one of the ways that you can integrate security into your different applications. And well, this embed TLS library includes support for PEM and has a software problem in how it handles that, which allows people to maybe take over your application if you're using this library. Another embed TLS example, this one's a timing attack. Because the library is not in the software handling your secret data very carefully and how it's doing AES encryption and also AES GCM for doing authentication, attackers will sometimes be able to extract secrets out of your multi-threaded application. This one's a little tricky to exploit. So this one that may be able, it actually does require some work to exploit this one, but it is possible. And so they put out a vulnerability announcement saying you really have to upgrade. Another example, Apache. So this is a very widely used web server, software, which is running, I don't know, millions of web servers around the world. And depending on your configuration, there's a desynchronization attack, which lets somebody do what's called a TLS upgrade to take over your web session. I love the fact that you can use something called a TLS upgrade in order to carry out an attack, but okay, that's how it works. And then another example, Mountain Duck, CyberDuck, these are some storage mechanisms like file storage mechanisms that you might be using. And these, again, have some problems in how they're handling TLS certificates, which may result in taking over more applications. I mean, already taking over your file storage is bad, but this can even be used to take over more than that. And then IBM has their message queuing middleware, MQ. And they say that, well, because of a mistake in what they were doing with certificate validation, you can take over an attacker can take over your TLS sessions. And this is used, this sort of middleware is used all over the place. So again, all sorts of disastrous consequences. Samsung, watches used to be something which is not part of your security picture, but well, these days they're important communication devices and also fantastic industrial espionage devices because they're right next to you listening to everything you're doing. And well, Samsung Internet for Galaxy Watch didn't do the right thing with TLS certificates. And because of that, they were actually pretty clear in this announcement about how disastrous this is. This is a critical misconfiguration that negates the use of HTTPS as a secure channel, allows for man-in-the-middle attacks, stealing sensitive information, or modifying incoming and outgoing traffic. That, I think, is a reasonable summary of what a typical TLS problem is doing for your application. All right. Oh, yeah, one more example. HCL Big Fix. So I don't have any experience with this, but from what I read, this is a tool which is used by corporations to manage software upgrades for all of their different devices. And apparently they just weren't using TLS internally for some important connections within BigFix, which presumably means that once the attacker has broken into your router, the attacker can then take over HCL BigFix and then install the attacker's software in place of your regular software upgrades and say goodbye to your entire security picture after that. What you see from all these examples is that there are lots and lots of applications that are trying to use TLS. These are just some recent examples of TLS going wrong. And there are many, many applications which are trying to use TLS and often getting it right, but often not getting it right. And this is an illustration of, again, TLS is supposed to be something where you integrate it into every protocol you're using, into every application you're using. And that's a big project. Lots and lots of applications. Your vacuum cleaner manufacturer has to worry about TLS. Another way to see that TLS is a really big programming project is to look at different languages having different TLS libraries for different environments. When people want to use TLS inside an application, they need some TLS software. And well, to integrate that into the application, it's sometimes a hassle to use a library written in another language. So people say, oh, I'm writing an application in Go. Can I please have my TLS library in Go? And so there's a TLS library in Go. And for people who use the Go programming language, it's a very common thing to use. And that's had its own vulnerabilities. And so there's lots of different applications and lots of different languages, lots of different environments. And they are all things which want to have their own TLS software. Another way to see how much software is involved in TLS, the traditional name for TLS, SSL, Secure Socket Layer. If you do a GitHub search for that, then you find more than 2 million results. And I looked at 100 random examples, and almost all of them were, in fact, TLS, SSL. There were a few which were some other things that, for whatever reason, people called SSL. But basically, there's clearly more than 2 million software like updates which are involving TLS. And this is a terrifying amount of software that we're talking about. Another example of how big this project is, if you look at Firefox, which has supported HTTPS for many years on the client side, that has some statistics of how many of the Firefox loads of web pages are using HTTPS. In other words, does the server support HTTPS? And that percentage has gone up over the years. 10 years ago it was 30%. 5 years ago it was 80%. And today it's, well, still 80%. Which makes you wonder what's happening with the other 20%. Like, are those web servers that just have HTTP and they don't even, nobody wrote the software to plug in TLS? Or maybe they're using software which does support TLS, like Apache or Embed TLS. I mean, whatever software stack they're using, maybe they could support TLS, but nobody set up TLS. And whatever the reasons are, there are 20% of the web servers that Firefox is trying to connect to where it's only connecting by HTTP and not HTTPS. It could sometimes be people just have HTTP URLs sitting around and haven't moved those over to HTTPS URLs. But there's a lot of user data which is not being encrypted with TLS at all. Now, from the attacker's perspective, this is great, because the attackers are looking around at everything they can possibly monitor. They're recording all of it. If it's just not encrypted right now, fantastic. If it is encrypted, well, maybe it's encrypted with pre-quantum cryptography, and then in some number of years, the attackers are going to have quantum computers and then break those ciphertexts. And which, of course, is the theme for today. What do we do about quantum attacks? And well, this is a problem, which TLS is trying to deal with this, but it's obviously having some problems. Now, of course, when you ask people, hey, what should we do about this? Then it's pretty clear what the answer looks like. I mean, TLS says, all right, for dealing with quantum computers, of course, we want to upgrade from, say, elliptic curve crypto to some post-quantum system plus elliptic curve crypto. Now, I'm saying that plus because a lot of times the upgrade to something post-quantum actually turns out to be breakable. And well, just in case that happens, you don't want to make your security worse. So definitely always do double encryption, double signatures. So do hybrids where you're encrypting with your old encryption mechanism and with whatever new thing, which hopefully protects against quantum computers. But just in case it doesn't, always make sure to use hybrids. If you want the opposite perspective on that, the National Security Agency, which has in the US, which has a long history of carrying out attacks, they would like you to not use hybrids. And so you can find their explanation of how to weaken your post-quantum crypto. Another thing that TLS says, beyond doing the post-quantum upgrade, which I should say, almost all of the use of post-quantum TLS and post-quantum crypto in general, people are ignoring what NSA is saying and doing hybrids. So this part about try to upgrade to try to protect against quantum computers, but in case it goes wrong, make sure to keep your old encryption sitting around so that you're not making things worse. That's what people are trying to do. And there's a lot of deployment of post-quantum TLS these days. Plus, when it's going wrong in, for example, buffer overflows or people failing to use it because they're doing something wrong in the certificate management, try to fix those software problems. And then when people are just failing to use it because they don't even know about it or because they're failing to configure it, then well, try to fix that. Try to get more and more people actually using TLS. Try to get that last 20% that has not been happening on the server side and whatever percentage on the client side and all sorts of other applications. HTTP is just one example. This all sounds reasonable. And I mean, what TLS is doing, of course, we should keep trying to do that. But it makes you wonder, could there be something easier? Instead of this gigantic project, is there something else that we can do, which is going to add some security, which is going to fill in the gaps and be something which is protecting people when TLS is failing to do so? And I mean, asking this question, again, of course, try to keep improving the situation for TLS, but can we do something else in the meantime that can actually stop some attacks that TLS is not currently stopping and that maybe in 5-10 years is still failing to stop? Well, there are some answers to this already. For example, VPNs. So a virtual private network, this is something where it's a different starting point. Instead of saying you should plug this into every protocol, every application, do a lot of programming, what a VPN does is just plugs into your computer's network. It just says, all right, before you send any data out on the network, right then we're going to take every network packet and encrypt it at that moment. And so the usual configuration for this is we visualize this as you have a tunnel set up, which is between you and some proxy for the VPN. So this is some server which is willing to accept traffic from you. Typically, it's configured with its list of people it's willing to talk to. And then you configure your VPN client to talk to that server. And then, okay, what happens is all of your network packets from all of your applications, as soon as they're going out on the network, the VPN software intercepts that and encrypts it, which means putting it inside the tunnel. Then it goes safely through the tunnel to the VPN proxy, which decrypts the traffic. And anywhere in between that, the attacker just sees the attacker's outside the tunnel, isn't able to see through the encryption. All right, from a perspective of how much programming do we have to do, VPNs are just much, much nicer than TLS because, again, they're just plugging into the network. There's a few different kinds of network software. For instance, there's Windows and Linux, and these have different types of network devices that you have to work with. So, okay, there's still multiple types of programming to do, and there's multiple VPNs for some other reasons, but it's much, much less than trying to plug something into every protocol, every application. So this sounds nice, and some VPNs already for years have supported post-quantum crypto. For instance, Molvad, Rosenpass, those are supporting post-quantum crypto. Lots of VPNs are based on OpenSSH, so you just do an SSH tunnel, and that, starting in early 2022, was using post-quantum crypto. Okay, so that's great, except, well, the typical TLS response to that is whatever VPNs are doing, it's not giving you end-to-end encryption all the way to the server. I mean, you have the proxy. There's this one server that is willing to accept your traffic, and you're sending all your data. For instance, it might be your corporation or your university says, okay, here's a VPN proxy that you can use. And from your home network, you send everything safely to that one proxy. But then the proxy is then forwarding your traffic to all of the different servers you're talking to. And the VPN is not protecting that forwarding at all. So if an attacker is anywhere on the network between the proxy and whichever servers you're talking to, or if the attacker is managing to take over that proxy itself, that's a nice juicy target for attacks, then your traffic is exposed and the VPN is not protecting you at all. Whereas TLS would say, oh, you're connecting all the way to the end server. TLS is encrypting data to each of the servers that you're talking to. Now, you can go to some extra work and say, all right, I know somehow certain servers which are also supporting this VPN, which lots of servers do, and lots of servers are willing to accept VPN traffic from anybody, as long as you don't ask them to forward anything. If you just want to send traffic to that one server, then there's lots of servers saying, yeah, anybody can do that. I'm happy to have my data encrypted from clients around the internet. And so you can just configure your VPN software to say, I'm going to do encrypted traffic to this server, which I know is supporting this VPN. And then if I'm talking to another server which supports this VPN, then you configure your VPN software to make another tunnel to that server. And great, this is protecting data to each of those servers at the expense of doing a lot of configuration work, which very few people do. I've occasionally done this sort of thing, and it's a hassle to manage the VPN configuration on both sides. I mean, on the side of the server, well, you have to set this up somehow and configure it to make sure anybody can connect, but not allow any forwarding because you don't want anybody forwarding through your server. And then on the client side, well, you have to somehow figure out which servers are supporting this, and you have to somehow say, okay, I'm going to configure my VPN software to connect to each of those servers. Wouldn't it be nice if all of that's just automated? I mean, just imagine that you get the same end-to-end protection for your VPN going all the way to the servers, which is what TLS also does. TLS also automates this. You don't have to configure your browser for each server you're going to talk to. You just click on a link and it does the tunnels automatically. But wouldn't it be nice if we had that end-to-end feature along with the VPN software engineering advantage of not having to change all your protocols and all your applications? So do some automatic end-to-end post-quantum encryption, not having to configure anything, and not having to touch your protocols, not having to touch your application. So combining the advantages of TLS and VPNs. And well, that brings me to PQConnect. So this is a boring private network. Boring is, well, digging a tunnel. And what this does automatically is what I was just describing. It figures out which servers are supporting PQConnect. Unlike, I mean, your VPN software, you have to manually configure this. PQConnect automates that. It says, I'll do the kind of thing a VPN does, a post-quantum VPN does, but I'm going to automatically figure out for you which servers are supporting this and then create tunnels to those servers. So you don't have to worry about that. All right, this is on the client side for supported operating systems, which is just Linux for the moment. It is just one step. For example, Debian in their new version 13 release, the Debian operating system, you just have to install PQConnect, and that's it. You don't have to configure anything else. You don't have to know which servers to configure. This is really the complete configuration. You just install the software, start it running, and then the client is going to figure everything out for you automatically. Now, on the server side, there's two steps because, well, the server has to have the software and has to say to everybody, hello, I'm willing to accept PQConnect connections. So there's two steps. One is to install the software, install PQConnect server. And then the other step is to, well, I'll show you how the announcements work at the protocol level. Is you broadcast this announcement telling everybody, yes, I'm willing to accept PQConnect connections. But you don't have to do something like have a list of clients that are allowed to connect. You want everybody to be able to securely connect to you. Just like when you're setting up a TLS server, then you don't normally say, oh, I mean, you can say I want to limit it to particular clients, but the normal way to protect as much data as possible is say everybody's allowed to make a secure connection to me. Okay, if a client is running PQConnect, if somebody's machine on the other end is connecting to your server and runs PQConnect, then it sees, aha, you're supporting PQConnect on your server, and then it creates a PQConnect tunnel. Let's look a little bit at how this works internally. So one example of a PQConnect server, which I'm running, is bench.cr.yp.to, which has various cryptographic benchmarks. And this one, well, in the domain name system, which is the standard name to address translation system that the internet uses, the bench.cr.yp.to name has, well, a CNAME record. The canonical name of bench.cr.yp.to is PQ1 something something something. It's longer string of what looks like random garbage, something.cr.yp.to. I'll just put part of it here with dot dot dots for the rest. And then that name has an address of 131.193.32.110. Now, normally, these are all standard kinds of information to put in DNS. If you look up DNS information for Amazon.com or any typical website, then you'll see this kind of data. And this is something which normal clients without any software upgrades are going to say, oh, yeah, I know what to do. That I look at the CNAME and then look at the A, which is attached to that, and there's the IP address that I'm supposed to connect to. I'm supposed to contact 131.193.32.110. And that's how your browser connects to bench.cr.yp.to. Now, a PQConnect client does something a little different. When this data is coming into your computer, then the PQConnect client software says, haha, I see what's going on there. This is announcing that the server is supporting PQConnect. And it's also telling me what the public key is for the server. And so now I'm going to set up a tunnel to that server and encrypt all the data to that server using PQConnect. Now, how does an application end up having its data intercepted by this PQConnect software to be put into the tunnel? Well, the way that works without any changes to the application is that the PQConnect software is feeding some slightly different data. Let me flip back and forth so you can spot the difference. Slightly different data to the applications on your machine. Instead of 131.193.32.110, it provides whatever application an address of 10.43.0.2, which is an internal address that the PQConnect software uses to intercept software from all of your applications. Your application doesn't realize this is happening. It just says, oh, there's an address I'm supposed to connect to, 10.43.0.2. Then the PQConnect software says, aha, here's some packets, which I will encrypt and send through the tunnel to the server. And the server similarly delivers the decrypted data to whichever application is running on that server without any changes to the application software. All right, all of this is relying on the DNS data to be secure, just like TLS does. People will often ignore this security problem, but there is a security problem with this name to address translation is something where if somebody substitutes a different address, I've put in the address of an attacker here. If somebody substitutes this data inside DNS and sends that data to your machine, then they will break TLS security. They can, for instance, they can send this data to Let's Encrypt and get a Let's Encrypt certificate, and then take over all the bench.cr.yp.to outgoing data and incoming data. And also, if they do this, then, well, your PQConnect client is going to look and say, oh, I don't see a PQConnect public key there. So it disables PQConnect as well. It breaks TLS security, also breaks PQConnect security. Now, what do we do about this? The ostrich approach is to say this is not a problem. Some better approaches are the following. There are some DNS security tools out there. And if you're using those tools, for example, DNS Curve, DNS Crypt, I've heard of something called DNSSEC. Doesn't work very well, but it does exist. And to the extent that people are using those, then that protection is applying to this. I mean, it's dealing with this problem in TLS and dealing with this problem in PQConnect. PQConnect itself can be used as protection for DNS because, again, its general purpose applies to, it's not something you have to change your applications to work with PQConnect. It just automatically protects packets. And so the DNS packets, if you're talking to a PQConnect DNS server, then it's encrypting that as well. And then the third thing PQConnect does to deal with this is says, we can actually provide some security that doesn't rely on DNS at all, because instead of using a name like bench.cr.yp.to, where you have to trust somebody to translate that into address information and eventually key information, what you can do instead is use a high security name, this PQ1 ... something complicated name that I was showing you on previous slides. You can just use that directly. And then PQConnect says, aha, there's that public key. And you're not relying on somebody translating the low security name into a high security name. All right, I'll talk about two little problems with TLS if I have a few minutes, and then I'll finish. One problem is that inside any particular TLS connection, which can go for days, weeks, months, you can have a continuous TLS session. And that session, it's not necessarily just one connection. You can have a TLS session can have multiple connections inside it. And then inside one TLS session, your key is lasting forever on the client and on the server. And then people are sometimes concerned about this. They say, ooh, this is not providing forward secrecy. So forward secrecy is where an attacker is somewhere during your session. An attacker is, for example, managing to compromise your server. And then as part of that, they see, aha, here's your secret key, which they can use to decrypt older data. And forward secrecy is the concept of, well, you should be forgetting keys, erasing keys as quickly as you can so that an attacker cannot go back in time. But, well, TLS does not support that within a session, does not have forward secrecy within a session. There's this advertising of TLS providing perfect forward secrecy. It is very, very far from perfect. And this is one of the basic deficiencies in it, which people try to address. They say, there's lots of advice saying, try to use short TLS sessions. Don't use a long-lasting TLS session. Try to have a TLS session only lasting, say, a few minutes or even less. And then, well, okay, then the attacker can only go back a few minutes in time. And it's not necessarily, I should say, an attacker who's like using some software compromise, which, I mean, hopefully we can get rid of that kind of problem by improving software, rewrite everything in Rust, et cetera. But imagine more extreme case. Imagine that like the secret police are coming in some authoritarian regime and stealing all of your hardware, which might sound kind of crazy, but some people have to worry about this kind of attack. Okay, so then there's lots of advice to keep your TLS sessions short. And that means that the session startup time in TLS is a big part of your TLS cost. If you run a TLS session for a long time, then it doesn't matter how much time you spend exchanging keys at the beginning. You're just doing some fast symmetric crypto after that. But if your sessions are very short, then suddenly the public key crypto to do key exchange is a big part of your time. And so that means that you have to worry more about how much you're spending on that, depending on how much cost you're able to allocate to TLS. And as a result of that, people will often say, yeah, let's try to skimp on what we're doing in the post-quantum key exchange mechanisms we're using for starting the session. Or another example, often people will not even have any post-quantum authentication right now because they'll think, oh, we can get that deployed before quantum computers are coming, and that'll be just in time because, of course, we're going to know exactly when quantum computers are available to the attackers. Okay, this sort of incentive, if you don't have this kind of pressure on starting your session, then you don't have to worry about this. You can say, oh yeah, I'll just do something which is high security, stop playing games with the security levels of things. Now, PQConnect says, all right, let's fix the underlying problem here. Inside any particular PQConnect session, the software is automatically making sure that every key is erased within 2 minutes. And so if an attacker manages to take over, then they can only go back 2 minutes at most in decrypting data. And this is something which, well, it relies on how PQConnect is designed, and then that makes this key erasure possible that without breaking your connection. You can keep having a PQConnect session lasting for months, and that's fine. One other problem, and then I'll finish up. Inside TLS, encryption is done only with short-term encryption keys. There's no long-term encryption keys in TLS. Now, this means that when you have your long-term server identity keys in TLS, that's something which only protects the identity, the authentication of your server. It's not used for encryption. What TLS does instead is has short-term keys for forward secrecy. Well, short-term, you were hearing on the previous slide, short-term depends on the length of your session, but in any case, that's the only way that TLS is providing confidentiality, is via those short-term keys that it's using to provide forward secrecy. And because the concepts of encryption and forward secrecy, those are all in TLS provided by just these one layers of keys. When TLS says, oh, I'm going to reduce security levels for my forward secrecy keys, that also means that it's reducing security levels for all applications of TLS, not just the forward secrecy context. It's reducing security levels for everybody. Now, PQConnect says, all right, let's separate these concepts. There are long-term keys which are used to identify the server, and we can use those for encryption because those are KEM keys, and you can use KEMs in order to identify servers, handle authentication, and encrypt. And then there's a separate layer of using KEMs for forward secrecy. And those short-term keys, well, if those manage to get broken somehow, then that's not compromising your outer layer of encryption. So you have better security than you do in TLS. All right, if you're interested in hearing more for Linux, you can use PQConnect now. If you're interested in the documentation, how to get it installed on your machine, just go to pqconnect.net. If you're interested in joining the new chat server to chat with other people about your experiences and want to make suggestions like, hey, when can we have a Windows version, or whatever your questions are, then just go to zulip.pqconnect.net. And if you're interested in a paper which says more about how this all works, that was at NDSS 2025 earlier this year, PQConnect Automated Post-Quantum End-to-End Tunnels. Thank you for your attention.